Hello friends, welcome to EC Academy.
In this lecture, let us understand capacitance estimation in VLSI design. First, let us understand load capacitance. Whenever we have an inverter or a CMOS gate, the total load capacitance at the output is called as CL, and this load capacitance is the sum of three main capacitance. Load capacitance on the output of a CMOS gate is the sum of gate capacitance, diffusion capacitance, and routing capacitance. Therefore, the load capacitance CL will be equal to C gate plus C diffusion plus C route. Now, how do we calculate any basic parallel plate capacitor? The capacitance can be calculated by C is equal to epsilon naught into epsilon R multiplied by A divided by D, where epsilon R is a dielectric constant or a relative permittivity and epsilon naught is permittivity of a free space, which is 8.854 into 10 to the power of minus 12 farads per meter. Here A and D represents the physical geometry of the capacitor, where A represents the capacitor plate area and D represents separation distance between the plates. Now let us see what happens to a MOS capacitor when we change the gate voltage VGS. First, accumulation mode, where Vg is less than 0. If we say Vg is less than 0, a negative voltage is applied across the gate. This negative voltage across the gate will attract holes to the surface. So, it behaves just like a simple parallel plate capacitor. So, holes which are accumulating near the surface acts like a parallel plate capacitor. The oxide capacitance can be given as C naught is equal to epsilon SiO2 multiplied with epsilon naught multiplied with A divided by T oxide. Second, we have depletion mode, where Vg will be greater than 0. If we say Vg is greater than 0, which means a positive voltage is applied across the gate. This positive voltage across the gate pushes the positive holes away and creating the depletion layer. So, as you can see here, if we apply positive voltage across the gate, the positive holes will be pushed away from the surface and it will form the depletion layer. And this depletion layer will be having a thickness of D. So, holes are repelled and depletion layer is formed. So, the depletion capacitance can be given as C depletion will be equal to epsilon Si into epsilon naught into A divided by D. This region will be acting as oxide capacitor connected in series with depletion capacitor. So, C naught and C depletion are in series. So, as you can see here, in depletion mode, the oxide layer and depletion layer are one after the other. That means C naught and C depletion are in series. So, in depletion mode, C naught and C depletion are connected in series. Now, let us understand inversion and capacitance variation. When we give high positive voltage, which is Vg greater than 0 across the gate, we enter the inversion mode. So, when Vg is very high with positive value, the negative electrons are pulled to the surface, creating the inversion layer, which is an N-type channel. So, Electrons form a thin layer at the surface. Therefore, N-type channel is formed. Now look at this capacitance variation graph. The vertex axis is C or C0 and the horizontal axis is VGS. We have three regions: accumulation, depletion and inversion. In accumulation, the capacitance is high, and when we enter depletion, the capacitance is low, and in inversion, the capacitance behavior depends upon the frequency. So, the capacitance increases for low frequency, and for high frequency the capacitance decreases in inversion region. So, you can remember, at low frequency inversion charge follows the signal, and at high frequency it cannot respond quickly. Now let us look at the formulas of gate and depletion capacitance. First, the gate oxide capacitance C0 will be equal to epsilon SiO2 multiplied with epsilon naught multiplied with A divided by T oxide, where epsilon SiO2 is the relative dielectric constant of silicon dioxide, which will be approximately equal to 3.9. So, you need to remember, the gate oxide will depend upon the gate area and oxide thickness. Now, depletion capacitance, that can be given as C depletion will be equal to epsilon Si multiplied with epsilon naught multiplied with A divided by D. Here D is the depletion layer depth and epsilon Si is the dielectric constant of silicon, which is approximately equal to 12. Now, series combination, the oxide capacitance and depletion capacitance are in series. Therefore, the gate to bulk capacitance CGB will be equal to C0 multiplied with C depletion divided by C0 plus C depletion. So, you need to remember, C0 and C depletion are in series. Therefore, CGB, which is gate to bulk capacitance, will be equal to C0 into C depletion divided by C0 plus C depletion. Again, you can remember here, at low frequency inversion charge can follow the signal, which means it can have the same capacitance, and at high frequency inversion charge cannot respond quickly, which means it will be having low capacitance. Now let us understand the MOS device capacitance. If we look at this transistor, we have gate, source, drain and substrate, and there are several capacitors that are present inside this device. Between gate and source, we have CGS. Between gate and bulk, we have CGB, and between gate and drain, we are having CGD, and also we have CSB between source and bulk, and CDB between drain and bulk. So, MOS transistors are having many capacitances that is represented in this diagram. Therefore, the total gate capacitance CG will be equal to CGB plus CGS plus CGD. So, CG will be equal to gate to bulk capacitance plus gate to source capacitance plus gate to drain capacitance. This is very important formula in VLSI. Now we will see how the gate capacitance changes in different operating regions. This table shows three different regions: off, linear and saturation region. Let us understand one by one. When transistor is off, CGB will be equal to epsilon into A divided by TOX, where epsilon is equal to epsilon SiO2 into epsilon naught, and approximately CGS and CGD in off state will be equal to 0. Therefore, total gate resistance will be equal to epsilon A divided by TOX. In linear region, CGB will be 0, CGS will be epsilon A divided by 2 TOX, and CGD will be epsilon A divided by 2OX. Therefore, total gate capacitance will be Cg is equal to epsilon A divided by TOX. In saturation region, CGB will be equal to 0, CGS will be equal to 2 epsilon A divided by 3 TOX, and CGD will be equal to 0. Therefore, total gate capacitance will be equal to 2 epsilon A divided by 3 TOX. Practically, we can approximate this value to 0.9 epsilon A divided by TOX. You need to remember, when the transistor is off or operating in linear region, the gate capacitance are same, and when it is operating in saturation region, the gate capacitance are different. So, we can say the capacitance change according to the operating regions of MOS transistor. Now, let us understand the second major capacitance, which is the diffusion capacitance. Now, look at the source and drain diffusion area. These diffusion regions forms the junction with the substrate. Because of these junctions, we get junction capacitance. The diffusion capacitance has two parts, area capacitance and peripheral capacitance. The formula can be written as CD is equal to CJA into AB plus CJP into 2A plus 2B, where CJA is the junction capacitance per micron square and CJP is the peripheral capacitance per micron, and A is the width of diffusion region and B is the extent of diffusion region. So, the first part CJA into AB comes from the area, and the second part CJP into 2A plus 2B comes from the perimeter. So, the diffusion capacitance has area part and perimeter part. So, you need to remember, area gives one capacitance contribution and the boundary or parameter gives another contribution. Now comes the third major capacitance, which is wire capacitance. In VLSI circuit, we connect different transistors using metal wires. These wires also has capacitance. If you look at this diagram, the electric field does not remain only directly between the conductors, but some field lines spread around the edges. These fields are known as firing fields, and because of these firing fields, we get the firing capacitance. Here, W represents the width of the wire, L represents the spacing between the wires, and T represents the conductor thickness. Also, H represents the oxide or dielectric thickness. Now, these dimensions affect the wire capacitance. So, remember, wire capacitance depends upon the physical arrangement of the wire and surrounding dielectric fields. So, you need to remember the shape, size and spacing surrounding the material of wire affect the capacitance. Now, let us understand wire capacitor of multi-layer. Modern VLSI chips have many metal layers. Here we are having layer 1, 2 and 3, and because these layers are close to each other, capacitance exists between them. We can have capacitance between layer 1 and 2, we can have capacitance between layer 2 and 3, and also we can have capacitance between nearby wires. The diagram shows C21, C23 and C22. Hence, the total capacitance is represented as C2 is equal to C21 plus C23 plus C22. Here you need to remember, a wire can have capacitance with nearby wires. So, in VLSI analysis, we must consider not only the transistor capacitance but also the interconnect or wire capacitance. This is very important when we estimate circuit delay. Till now we have studied different types of capacitance in CMOS circuit. We studied gate capacitance, diffusion capacitance and wire capacitance. Now a very important question, why is capacitance so important in VLSI? More capacitance means more charge to move. When capacitor is large, we need more charge carriers to charge or discharge the capacitance. So if capacitance increases, the amount of charge required also increases for the same voltage. More capacitance means more delay. Now, if we have more capacitance, the transistor needs more time to charge or discharge. Therefore, the circuit becomes slower. More capacitance means more dynamic power. In digital circuit, capacitances are continuously charged and discharged when the circuit switches. Every time the circuit changes from one logic level to another logic level, the energy is involved in it. Hence, we can say more capacitance means more dynamic power. Critical for high speed and low power VLSI design. In modern VLSI design, we want circuit that are fast and low power. But large capacitance work against both of these, which means large capacitance can increase delay and dynamic power. Therefore, when designing a VLSI circuit, we try to control and reduce unnecessary capacitance. This is about capacitance estimation in VLSI. Hope you have understood the topic. Thank you.